Hello, everybody. I hope that I sound okay. Everything is fine. So for today, we will try to chat and talk and have a kind of a plea how to interact with our systems. What is HPC? What is HTC? And how? What are the best practices in interacting with the clusters? Before we will go to the essence of our meeting, let first me tell you a little bit about myself, about the history, what happened, etc., etc. So I have started to work with HPC as a part of WestGrid, and WestGrid was initially formed by the University of British Columbia, SFU, University of Calgary, University of Alberta, and University of Saskatchewan. These were the initial founders of HPC within WestGrid. Later on, University of Saskatchewan joined, and University of Victoria, and all other smaller institutions. And this happened roughly 20 years ago. And at that time, we deployed various systems. So everything was geared towards slightly different workflow. For instance, in Calgary, we have a pure parallel system, but it was distributed. However, in the University of Alberta, we have a quite substantial shared memory system. And it happened roughly 2002 to 2003, where we deployed these major installations in these institutions. At the same time, slowly, but HPC environment started to change. The InfiniBand started to be evolved. Multi-core systems started to be deployed roughly in 2005. In 2010, the first GPUs started to be used as an accelerator for the computation. So the architecture started to evolve rapidly around 2005, 2010. And that was more or less the time where WestGrid also joined the other consortia, and we formed this Compute Canada, which was a national platform. And right now, I believe 2 years ago, Compute Canada basically transitioned into the Digital Research Alliance. And currently, we are running, I believe, 5 different sites. And in essence, all of them look very similar, because the modern HPC architecture, hold a second, page down, looks more or less like that, right? So we have plenty of compute nodes with there's some specialized compute nodes, small memory with the GPU, and everything is basically interconnected with this fast interconnect. And in addition to this, we have a storage which is attached to all these compute nodes, and they all communicate via this fast interconnect. So this is how a more or less HPC architecture looks in a nutshell in most of the systems which are available at the moment in Canada. And in essence, this is more or less the way the clusters are built at the moment. The entire difference is basically how they are connected, okay? What is the interconnect? So if this is fully interconnected, or if this is some blocking factor, but in essence, that's how the current HPC, HTC architecture looks like. So now the question, what do you as the user see when you connect to the system? So definitely you see the login nodes, you see the data transfer nodes, you see all the compute nodes which are available, you see all the special nodes, and you see this interconnect between the nodes. However, there is plenty of stuff when you as a user do not see. These are all administration and management nodes, all of services which we are running behind the scenes to make the system smooth and performing. You don't see the nodes which are serving the file system. You basically see the file system. You don't see the quantity of hardware which has to work in unison to support access to the files. And of course, there are some special nodes reserved for the monitoring, provisioning. And obviously, you don't see this entire hardware which is servicing the network. So you don't see the switches, you don't see the cables, you don't see anything of that. However, we as a system administrators, we see this, and very often we're starting to have some issues, problems, and then that's why we need these best practices, how to interact with everything. So, and that's what is right now the most important, okay? If you are working on your workstation or on your laptop, this is only you. So whatever you do affects only you. With the HPC, HTC cluster, you are interacting with all the other users, and you are also interacting with us, okay? And the performance and stability of the system, of course, affects you because your code runs slower. You are angry that your files are not written on time, but it also affects us because we need to solve this performance and stability issues, and sometimes they are incredibly difficult to track. So right now, let's define what is HPC. So in essence, HPC, these are the tightly coupled parallel jobs requesting multiple nodes. And the communication between the nodes is based with the message passing interface layer. On the contrary, HTC will be basically, that's an independent, mostly sequential jobs, which are run on a single node, which don't need access to a different node. And they can be basically individually scheduled on many different computational resources. So if the system is pure HPC, so right now I will ask you a question, okay? I will put in chat HPC, okay? And then I will put another, and I put HTC. And now if you can react to HPC and HTC with a thumb up, we will basically, all of us will be able to see how we identify ourselves, okay? Okay, so far we have HPC is winning, but HTC is picking up. So, hold a second. Okay. So right now, if we have a system on which we are mostly running HPC workflow, the situation is quite easy to control, because if I'm requesting many nodes on my entire cluster, I can run maybe 10, maybe 20, a handful of applications, and it's much easier to track what's really going on and how to tune these applications in order to be effective. However, when we are starting to go into the pure HTC environment, then we are starting to have a little bit more problem, because there is much more jobs running on a system, and very often it's quite difficult to identify which job, which node is causing our stability and performance problem. So let's start how we will use the cluster. So login nodes, right? You log in, you are getting a prompt. So the best practice is to use login nodes for just interactive sessions, editing files, compiling, editing, moving stuff around, navigating, submitting jobs, etc., etc. You can use login nodes for the short testing. However, if you have already satisfied or the job or your tests need much more time than, let's say, 5, 10, 15 minutes, the best practice is to basically start using interactive nodes and use the batch system available in the system. When you are doing the file transfer, use data transfer nodes. They are dedicated, they have a very good connectivity to the file system, they have good connectivity to the internet, and moving data from your workstation or from other clusters to the cluster you are currently working on, you should use this data transfer nodes, and the best way to interact with the data and moving them around is basically a globus. So if you can also install Globus Terminal Connect on your workstation, on your laptop, and use this. Now, the last point to interacting with the login nodes and the data transfer nodes is basically my point to clean up when you are done. So when you stop working, make sure that all the processes which you have started somewhere in the background are finished and they are not hanging around, because this hanging around sessions very often cause us some problems. Right now, let's go to how we will deal with the file system. So typically, when you logged in, you see home, you see project, you see nearline, and you see the scratch. Home, and since this is a shared facility, we unfortunately have to impose the quota of on the size and number of files every user can use. So these are the values taken from the Alliance webpage, and these are the quotas for the most of the currently computers or Alliance systems. Home, as the name suggests, is your private space. So in home, you should store mostly the stuff which is yours. And this is your source code, this is your, these are your thesis, this is your paper you are working on, these are the graphs, tables, static data. In essence, this should be a very static type of the data, right? Because the home is being backed up. So in order to have the efficient backup of the system, we don't need the files which are changing rapidly. But home is small, okay? And home is not dedicated or designed for sharing. If you would like to share some data, you are running the same code within your group, then the place to put this software or the data you would like to share is the project file system, okay? That's this project. Nearline is basically, that's a tape-based file system, and this is dedicated for the long-time preservation of your data. Moving files to nearline is easy. Moving files from nearline is time-consuming. So whatever you are putting in a nearline should be basically something which you will not be needing for the computation for the next month, half a year, maybe even a year. And finally, the scratch file system is, so again, home is being backed up, project is being backed up, and nearline is being backed up. Scratch file system, as the name suggests, you have a lot of space there. But this is, and it has to be dynamic, it has to perform fast, and on many systems, basically, the policy is that all your jobs have to use the Scratch file system. And there is no backup. So whatever you are losing within Scratch file system is not being backed up. So if you remove the file, or you've erased the file, or you've somehow overwrite this file, this is gone. So we are very sorry, but the data is gone. Okay, so you have to be quite careful with your commands, how, like move, like remove, etc., etc. And now, if coming back to the performance, okay, this is the email which was being sent to me a couple of weeks ago, okay, by a very seasoned system administrator. So the problem sometimes is that having so many users, so many jobs, so many different workflows, sometimes it's even for the very seasoned system administrator, it's quite difficult to diagnose the problem. So that's my plea to everybody, that let's basically be careful. Let's make life easy for you, and let's make life easier for us. Okay, so right now, what are the best practices to interact with the file system? So if you're running for HPC or HTC for workflow, it's always a good idea to have a few checkpoints of your jobs, okay? So in essence, checkpoint is basically saving the state of the simulation periodically. So whenever you would like to start continue the simulation, continue this job, you don't start from the beginning. You don't start from the initial conditions. You basically start whenever from the point somewhere within your simulation. Again, checkpointing is creating either one checkpoint file or multiple checkpoint files. So how often you will checkpoint your jobs is quite important. So let's assume that you are running something for a day, and then you will be restarting this the following day. Then checkpointing frequency should be an order of a few hours. There is no point of checkpointing too often, because you are slowing your workflow, you are slowing your computation. The other issue with the file system is avoid excessive logging. I have seen people who are basically running their simulation, and every second they are trying to put, oh, I'm going, okay, I made next iteration. You have to remember that the file system is Scratch. This is usually Lustre. However, the GPFS is also being used. These are all network-based file system. So if you are writing to a file, you have to contact the metadata server. The metadata server has to contact the OSS server. The OSS server has to find the space on the disk and do the write. So there is a multiple communication between the node you are computing on and the file system. So the less you are the less files you are putting there, this obviously speeds up your simulation, right? So please avoid excessive logging. Okay, I know that when you are starting to work on your workstation laptop, you would like to see this. Okay, it's going. But when you move your workflow to the cluster, you can basically decrease this frequency. Okay, so there is no point of every second touching small, putting a small amount of data to some file, which tells you, oh yes, I am going, all right? So that's my plea. The other story is that most of this parallel file system, like Lustre and GPFS, they don't deal very well with plenty of small files. They are perfect when your data set is a big file, then they are perfect. With the small, tiny, an order of kilobytes or megabytes files, this is very, very stressful on the file system. So that's why we have this quota. Usually in Scratch, that's 1 million files. Very often, for some workflows, that's not enough. So then we are suggesting to use the local on the compute nodes disk, and this is always available via this environmental variable slurm underscore tmpg. Some systems offer a special file system for this kind of a workflow when you need to create multiple small files, but not all of them. However, right now, since we will be deploying new installations early next year, I hope that we will have more variety of the file systems available for the computations, and we will be able to address this many small files. And if you are not sure, please talk to us. Okay, we are in this. We are here together. And no, I am not doing any kind of examples, because there is very extensive documentation on the Alliance documentation pages, on our local installations. So read the documentation, look around, and if you are not sure, please contact us. Now, installing and working with the software, right? So the best practices working with the software. Right now, most of the current systems we are using, we are deploying software and we are creating these modules which basically set up your environment. So look around, modules available. Plenty of software is being installed on a system. If there is something missing, please talk to us, and we either install this or we will navigate you how to install your software either in home or the project space using just these modules, right? So you will load base modules, then you will download your software, and you will compile your software using the compiler of your choice. Most of the time, not most of the time, almost everywhere, we are offering multiple compilers and multiple versions of the compilers, multiple versions of Python, multiple versions of other packages, which are basically your base to build your environment. So be consistent. So when you are loading the modules, don't try to mismatch the modules you have loaded. Try to be always within a particular module tree. And when you're submitting the job, always start fresh. Okay, so start from the environment which you already are familiar with, comfortable with, which has been verified and checked, right? Because sometimes when you submit a job, Slurm job always inherits your current working environment. So it can lead to some kind of issues of your code. That's why I am suggesting all the users to list their modules which they are using in the job script. So it will give us ability to diagnose and easier diagnose and easier find the problem when there are some issues. Okay, so that's the software. I'm not sure if I am moving. I think that I am moving okay. Okay, now how we are interacting with the scheduler, okay? Most of the current systems are running Slurm. This is the most popular scheduler in the HPC, HTC environment, right? Almost all systems in the Alliance and all the systems which I know, which are locally installed, are running Slurm scheduler. But whatever the scheduler we will be running, or whatever the underlying scheduler is, please avoid the following. Don't ask scheduler every second, is my job running, is my job running, or is my job still queued? Because, okay, if one user is asking what is the state of the queue, the scheduler will respond immediately. But if there is 1,000 people having watch minus n equal 1 as queue, then the scheduler is all the time trying to satisfy your request, and it slows down the scheduler agility to work effectively. That's my plea to other users as well. The number of jobs in the queue. Okay, try to be reasonable. Okay, I am not saying that please submit only one and that's it, but be reasonable. Okay, because when we are looking at the jobs which are running, we would like to see this on one, maybe two, maybe 3 pages of output, not thousands of pages. In order to have effectively jobs being effectively scheduled, always try to start with, if you know that your job will end up within 24 hours, ask for 26, 28, 30. Don't ask for 7 days. For such a job will be easier to schedule. So the shorter wall time, the better. Okay, this is the easiest. Sorry, such jobs which are asking for a short wall time are always much easier to schedule than the jobs which are trying to reserve a lot of resources for a long, long time. Okay. And be as specific as possible. We'll go to the example of the submission script in a moment. Be also very precise. How many resources are you requesting? So how many cores, how many nodes, how many GPUs? I have seen plenty of jobs that people are asking for multiple nodes with all the GPUs available there, and they are using only one. And then they are complaining that their jobs are in a queue for a long, long time. If you are doing HPC or even HTC, this is very useful utility. You can use job arrays for the HTC workflow. So if you have many very similar jobs which only differ slightly by the input parameters, look at the documentation how to use the job arrays. For the HPC workflow, job dependencies are also very, very recommended. I am not giving the example how to use the job arrays. I am not giving you examples how to use the job dependencies. Our documentation is incredibly thorough in this with plenty of examples. So my plea to you guys is basically read and for documentation, try to follow the examples, and this documentation is quite thorough and good. Okay, so right now I would like to go a little bit into the how the script should look like. So that's the typical HTC, so high throughput computing job script, right? I am always asking for the single node. Please use this. So these are the variables which I would like to see in most of the HTC type of environment. So number of nodes, how much memory you would like to use per CPU. You can use just mem, because that will be full memory per your run. And then right now, most of the software, available software is multi-threaded, right? So you can basically use it's not a sequential serial process. You are just basically splitting your computation into the smaller threads. So read the documentation about your software which we are using, and match the number of, they are always suggesting how well, with how many threads the job performs the better. So ask for this for number of CPU, the number of cores per your task, because that's a single task. And export this variable with slurm CPU per task to your code. What else? Okay, I think, and of course you have to submit, use all the other options such as account, mail, location of output and error files. But these are very often mandatory stuff. But I would put the emphasis on the number of cores and how much memory you need. And this number of cores, the number of threads which you will be using, should match your code. Very often I have seen that you're asking for, let's say a user is asking CPUs per task equal 4. That's how how it's in this example. And then if his Python code is starting 20 or more, or even sometimes hundreds of threads. And of course, the scheduler will only give 4 cores. So then instead of doing effective simulation, you are just basically switching from one thread to another thread. And your simulation is going slow, and you are getting frustrated, and it doesn't work as you were expecting, how it was working on your laptop or your workstation, where you have basically, when you are running interactively, all cores are available for your code. So be careful when you are moving your code from your personal workstation to the cluster, always to look how many threads you would like to use. Okay, so that's the best practice, and I am kindly ask you to be careful and to do that. Okay, so right now how the HPC script looks. Okay, so in typical HPC job, once again, for how many nodes do I need? And then for this variable n task per node, okay? N task per node is how many MPI processes I would like to start per node. Since you would like to have your HPC job giving you predictable, consistent results in terms of runtime, it's good not to share the node with anybody else. Because if you are sharing a node, this other job which is running on the node which we are sharing with this job can do some extensive I/O, slowing your I/O. The job can start hammering the local disk or hammering the network with some I/O or communication request, slowing down your simulation. So within the HPC workflow, always try to use full nodes. Okay, and I believe that right now all these new systems, they have more and more cores, but try to tune up your application. Try to find this sweet spot when you are basically using all cores on a node, because then your results will be consistent and predictable. finally, it's not the last slide, but last example is a hybrid kind of a job script. There's, let's say, for Gromax software. Gromax is a molecular dynamics simulation software developed in Europe, and it's widely and very popular, used by the chemists. Very often for some kind of an input, some kind of a MD simulation, you would like to use MPI connected with the multi-threading. So in this case, I am changing this variable and task per node, right? So I am starting to, I can start as I can ask for few nodes. On every node, I will ask one MPI process, and the rest of the processes will be running as a thread. So then again, for CPU per task, okay, that's how many threads I will start per MPI process on a given node. And again, it would be very useful if you can utilize the full node. It's not a must, but I can start 2 MPI processes per node and for a few threads. So you have to be basically, then you have to make this calculation and estimation that n task per node multiplied by the CPUs per task should basically match how many cores I have in a system on a given node. So let's say for the nodes which have 32 cores, which are quite popular, Skylake architecture, I can ask for 4 tasks per node and 8 CPUs per task. And then 4 multiplied by 8 will give me 32 processes per node, and that's how many cores do I have. So that's the final example. I will appreciate we will appreciate your input. Please contact us at the support at tech.alliance at Canada. You can always contact and talk to your local support team at your university. And let's stay in touch and always have a conversation. Whenever you are starting or whenever you are having any problems, don't hesitate to reach out to us. We are here together. And we would like to make your life easier and our life easier. Okay, so thanks so much.